There are some more assignments on the horizon you can see here. I did want to let you know, I just kind of adjusted our schedule a little bit from what's in the syllabus after some of the other instructors and the course coordinator decided to shift what all was going to be on your remaining test prior to the final exam. So we've got a test in class, let's see, 2.5 weeks from now, on Tuesday, April 26th, which is the next to last day of class. Thursday, the 28th, is our final exam review day, and then our final exam is Tuesday after this. It's not at 7:30 in the morning. It's at 7 to 9 p.m. on whatever that is, Tuesday, May 3rd. Let's see, do I have that on here? I just want to go. Yeah, Tuesday, May 3rd. So, in any case, we're going to finish up, let's see, this week we'll just get up through a little bit with 7.7, although I'm not going to have the lesson for it due until after the weekend, just so you have a little bit more time to get caught up on everything else, work on the assignments tonight, and do a little bit more looking ahead. So next week in class, we're going to cover, let's see, was it 7.8, 9, and 10? And that's the rest of chapter 7. And the exam 3 is mostly just going to cover chapter 7. There will be on it, and this was the source of the discussion in class, or in email over the last week, the exam number 3, which is, like I said, 2.5 weeks out, is basically going to cover chapter 7 material, or module 7 material, which we're finishing up next week, plus just a little bit from section, let's see, 8.1 and 8.2, which is some right triangle trigonometry, which if you've done anything with trigonometry before, this is the stuff that you've probably seen. So it shouldn't be too intimidating in that sense, and that'll be the last kind of stuff that's covered on the midterm, or the exam 3, which is that Tuesday the 26th. However, the day before that midterm, we'll do a little bit of review, but also a little bit of preview of what we're doing, like just one last section. This 8.3, which we're going to talk about a little bit on Thursday the 21st, and a little bit on our exam review day, which is use of trig identities, which are kind of fun. They're just, because sine and cosine and tangent, which we haven't talked about the tangent function yet, that's one of the things that's in chapter 7 upcoming yet. Sine and cosine and tangent are all different combinations of relationships between some of the same measurements when we're talking about either points within a circle or measurements in a triangle. They all involve different combinations of the same thing, so there's lots of relationships between them that can be stated, and that's kind of useful for changing an equation that somebody might have known in one form into an equation using different functions. So that doesn't happen with, like, there's like square roots. You can't like change a square root into something else because square roots are just square roots. But sine measurements involve like, distance from the center and a distance vertically in a circle, which, if we're thinking triangles, that's two sides of a triangle, and the third side of the triangle, Pythagorean theorem, is related to cosine with the radius. And so all these things are interrelated with one another. And so trig identities is just, it's a way to, it's just a lot of practice with, hey, what if we mess around with this equation? What else can we make it look like? Or which of these are actually true statements based on some of the facts you know about these, specifically sine and cosine functions a lot. And there's a whole ton of them. There are some sections in math that are kind of like this. There are thousands, probably an infinite number of potential what are called trig identities, just true statements, relationships about them that you could write just because there are equations and you can make equivalent equations by do the same thing to both sides. There's lists of some specific kind of keys that you'll find in the backs of books. This is the same as in calculus. There's like tables in the backs of books where you can just look up all these different relationships, like what the results from tedious otherwise computations are, just for a quick reference. Trig identities are one of those things that's quick reference. You can look it up. As long as you're kind of familiar with looking for certain sorts of things, these aren't the types of things that, other than maybe a few that are easy to remember, you'd want to have memorized for any reason. They're just like, oh, there's some rule about that. Let me look up what it is, because literally nobody remembers all of them, unless you teach it every single term and that's your specialty. And I don't remember all of them, and I've taught this a lot. It's just, oh, there's a rule about that. Let's look it up. Because that's a bit beyond the easy to remember. There are some things that take a lot of deriving these relationships from doing a 30-step equation. Like, okay, so this is related to that. I know there's a rule about it. What's the rule? Oh, there's a plus there and a something, and I can just change one thing into another. Great. Save yourself all the recreating the wheel. But from time to time in a math class, you'll see the derivation of some of them, which is kind of cool. As a part of, it just kind of happens to show up while you're trying to do something else. But as I said, trig identities, it's long, and if you look at a whole list of them, it looks really intimidating. Don't worry, I'm not going to require you to memorize a bunch of things. It's just things to know kind of that they exist, and that there's usually a resource to look them up, and we'll have a little bit of practice at using them. And that's all we're going to be doing with them between the day before exam 3. So next week Thursday, or not next week Thursday, but this Thursday the 21st, and the day after exam 3. We'll take a look at a few of them just for like fun, practice, whatever you want to call it. A little bit of both of those days, but the rest of both of those days will be test review, one for exam 3 and one for the final exam. So, in any case, let's see. For today, we left off talking about some things in 7.6. I want to take a look at some of the end of the lesson, which was due already, just to kind of go over some of that, which I know you already worked through. We talked about the car going around a track and modeling things with that. I'm going to skip over the backwards clock because that's weird, but I did want to talk about this periodicity. So there's not a title up there. Just the idea of a periodic function, something that repeats. So if you're looking at a graph, it's about this horizontal sort of repeated pattern, happens over and over and over. Like if we've seen pictures of whole sine curves, they just kind of do the same thing over and over and over. It's measuring vertical distances as something rotates around a circle over and over. Obviously, you're going to get the same sorts of values over and over as outputs to that. Same with cosine, same with tangent, which we'll talk about soon, but period in a graph, you can see, and let me make this, there we go, a little bit bigger. Period in a graph, if you have a periodic function, something that repeats itself regardless of what this pattern is, and if we know a formula for it, is how long it takes for the pattern to start repeating. And it's that minimum amount of domain that you have to go through until the pattern starts repeating. So in this graph, for instance, I can measure that by picking some key easy to recognize points like those top endpoints there, or I can pick the bottom endpoints. Those are really, there's not like a easy to pinpoint spot in between. But either of those, if we take a look and measure along the x-axis, are 8 units apart. So like peak to peak or bottom point to bottom point, whatever you want to call these, they're about 8 units apart. So we say the period of this is 8. Sine and cosine functions, the way they go, when we have just like y equals sine of theta, or f of theta equals sine of theta, whatever you want to call the vertical and horizontal variables. Since it's measuring this vertical distance above the horizontal as you rotate around a circle, where the input is just the angle, if that's what it was in the particular function, like just sine of theta, that's going to have to repeat every 2 pi units, every 2 pi radian measure angle as you go around. So the period of a sine function that's just sine of theta or cosine of theta, it's just measuring the horizontal part, is just 2 pi. Now if you change some things about that, like we were talking about with, well, let's see, let me just go back to this toy race car. If we were writing something about its distance just based on what angle it's at, I'm going to have to erase some of this person's. I don't know if they think that ASU has people to clean up classrooms, but All right, so if this is that racetrack with a radius of 4 units, what is it? Feet. Feet. So it's 4 feet from the center to the edge, or the car is always 4 feet from the center of this racetrack as it goes around in a circle. If I wanted to measure, and just so I don't, the distance to the right, to not go completely away from what it said there. If I wanted to measure the distance to the right of the center as the car travels around this direction, it starts out 4 feet away, and then it gets closer until it's 0 feet, and then, well, 4 feet away, but in the negative direction, so 4 feet left, and so on. If I'm tracking that distance, I can be talking about, here, I'll just call it f of theta. If f of theta is supposed to represent the horizontal distance, either to the right or to the left, where positive would be to the right, negative to the left, we just use the cosine function for that. The only thing is that's if I measure in radius lengths. So if I want to talk about number of feet, I'm going to throw in this 4 there, right? But still, regardless, it takes theta going from 0 to 2 pi to go through the whole set of values before it starts repeating again. So 0 to 2 pi is 1 period worth of values, or the distance between those two, 2 pi units, is the length of the period. So we say that cosine of theta has a period of 2 pi because it takes 2 pi units, and normally we go 0 to 2 pi, but you could also talk about like 1 to 2 pi plus 1, or wherever that is, or pi over 2 to 2.5 pi, 5 pi over 2. Any set of units that are 2 pi apart would have the same exact values, because, like, you know, the car being here, having just traveled this far, versus the car being here, having traveled all the way around and getting there, it's still 2 pi apart in terms of its the next time it could be there, the next time it could have that specific value or have gone through all the values in between would be in that spot. So the period of this cosine of theta is 2 pi. Now this means that if I'm measuring in feet, I can tell from this being here that my values, output values for this, are going to be between 4 and negative 4. It's going to go through all the ones in between, hitting 0 sometimes also. But graphically speaking, what that tells me is that if I were graphing this, f of theta, with theta along this way and just not around the circle, but if I were just say, okay, so what happens if I go from 0 to 2 pi? What sort of values does this have? Well, it starts at a positive 4, goes as low as negative 4 when I'm at pi radians, and by the time I'm back to 2 pi, I'm back where I started. And it goes through all these values in between. And we kind of saw what this curve ends up looking like. It's symmetric. So kind of like a parabola here, but you know, it changes concavity more times. But it's symmetric left to right over that period 0 to 2 pi. I could keep going around over and over and over again. But what I wanted to point out about this 4. This 4 here represents the radius of that circle, or it also tells us the maximum distance away from 0 that I have. If I see this function, like, oh, this is going to go up and down by 4 from, you know, the center. I have up as high as positive 4, down as low as negative 4. This 4 is called the amplitude. These two words are kind of key in describing period and amplitude, are kind of key in describing trig functions, because they repeat themselves. So if you know how often they repeat themselves and what sort of values they go through, how high, how low, because they are wave functions. Say, oh, we'll go, it waves up and down by how far? Well, 4. That's not the height top to bottom of this, but that's how far above and how far below. It goes 4 up and 4 down from, in this case, this horizontal axis, if I'm graphing it that way. But if you remember, we talked about another question in class on Tuesday. I'm like, what day of the week is this? On Tuesday, where was a Ferris wheel, and we were concerned about how high above the ground somebody was. Their vertical position relative to the ground, which I'm not going to talk about that with horizontal because that'd be weird, but vertical position relative to the ground versus vertical position relative to the center of the Ferris wheel, which those are both sine functions, but one has a little extra number thrown in. So thinking about that Ferris wheel question, I'm just going to, I don't remember exactly where it was, so I'll just make up a new one. But let's say that the Ferris wheel was, let's see, what would be a good size for a Ferris wheel? You don't want to make it too small. 20 feet in as its radius, still kind of small. But that the center of the Ferris wheel was 24 feet above the ground. So let's say I had a Ferris wheel 20 feet as its radius, and it's 24 feet above the ground. So if I want to model vertical position of someone as they travel around this Ferris wheel, they're not going to be under the ground at any point in time, luckily, because that would be a mess. But they are going to go through all the same types of values, just relative to this spot, as they would if that were on the ground. If I wanted to model the height vertically, just relative to the center of the Ferris wheel, the vertical position, like where are they, how high or how low below, how far above or below the center of the Ferris wheel is someone at any angle. Just let's talk angles, not speeds. I can talk about, well, let's see, that would be a sine function if I'm concerned about vertical position, just our definition of a sine function. It's got a radius of 20. So that one had a radius of 4. And so, let's see, I'll call this g of theta. I could say that this g of theta equals 20 times sine of theta models my vertical position relative to the center of this 20-foot radius Ferris wheel, right, relative to the center of it. So I could be up to 20 feet above or down as low as 20 feet below it. But if I want to talk about vertical position relative to the ground instead, I should have picked G for that one. Oh well. I would just need to take all these heights and just move them all up. Just like the center of this Ferris wheel is 24 feet above the ground, I want the center of this sine curve, if I was graphing it, to be 24 feet higher than the x-axis. Not the bottom of it, but instead of sine curve for function g, which would, at angle 0, I'm 0 feet above. By the time I get back to pi, I'm also 0 feet above the center. And then at 2 pi, I'm at 0 feet above the center. Where at first, I'm above the center, and the second half of that, we're below the center, right? So it's this sort of section of a wave. This would be g of theta. So I'm above and below the center. If I want to talk about how far I am above the ground, all I have to know is like, oh, well, the center is 24 feet above the ground. So however far I am above or below the center, just add 24 to that. That's how far I am above the ground. For instance, at the beginning, I'm exactly 24 feet above the ground. Then I go up 20 feet, down 20 feet, down another 20 feet. So at minimum, I'm at 4 feet above the ground, and at maximum, I'm at, let's see, 24 plus an extra 20, 44. So instead of going between, like this function does, 20 and negative 20, I'm just 24 higher than that. So that puts us up at 4 to 44. 4 through 44. That sounds like a lot of fours. So if I want to graph this function h, I don't need the bottom quadrants at all. But the center of the Ferris wheel is at 24 feet above the ground. My height's going to be equally above and below that 24 feet. Between 0, let's see, pi and 2 pi. So if I think about, well, that's the center of the Ferris wheel, how high it is above the ground. For the first half of my trip around, I'm higher than 24 feet above the ground. For the second half, I'm lower than 24 feet above the ground. But it's the same pattern as that one, in that this was 20 feet above that x-axis, 20 feet above the center of the Ferris wheel. This is 20 feet above the center of the Ferris wheel, which puts us at 44. This was 20 feet below. We're down 20 feet. This is down 20 feet from that, putting us at then 4 feet above the ground, right? So this, both of these functions have a period of 2 pi. It's still talking about just rotating. We're not talking about time to go around. We'll talk about that in another example. Like not about speed, but just as the angle increases, our angle of motion around the Ferris wheel, or the angle of the car around the track. But tracking angle around a Ferris wheel, if we're tracking our vertical position, how high I am above or below the center of the Ferris wheel or above or below the ground, it's the same relative to something sort of numbers. It's the same shape, just shifted. So I've got a function here, just 20 sine of x. To move that whole graph up, and again, if it continued, it'd still be the same pattern. To move the whole graph up 24 units like that, 20 sine of theta plus 24, just vertical shift of 24 units. Vertical shifts work the same for all sorts of functions. It's just that kind of added on at the end or subtracted if it's a shift downward. Because in terms of computing, like if you're doing computations manually, order of operations wise, the last thing you would do would be that. Put in a number, do a sine computation, multiply by 20, and then add. Adding and subtracting comes last. So with or without that, that makes the difference between directly the y value or the output value that you get. So this plus 24 at the end tells us that this graph has been shifted upward by 24 from where it would be without it, which without it, it's kind of got this, not exactly symmetry, but the middle of the graph, top to bottom, is the horizontal axis for a sine function. It's called the midline of the graph. It's not that it has symmetry over it, but the parts above and the parts below are just as high above and down below, just as far as one another. The wave's amplitude is cut in half by this midline, 20 above it and 20 below it. Same here, 20 above and 20 below. I mean, if you could like fold this and flip it over and make it all match up on itself, it is nice and symmetric, but just not like a reflection sort of symmetry. Oops, sorry. There we go. So in any case, we've got period, we've got an amplitude. this number here represents the midline of this graph, but it's also just a vertical shift, like x squared versus x squared plus 5. It's a vertical shift of a parabola. Sine of something versus sine of something plus 24, it's just a vertical shift of that sine curve. The whole thing moves upward. But a nice way to describe what that is it moves the midline of the graph up by 24. So do I have that word written anywhere? I've got period, amplitude, midline is the other word. That's usually used to describe sine and cosine curves because they go equally above and below some horizontal line, whether it's the horizontal axis if you haven't shifted anywhere or something else if you have. So that one, our midline was 0. This function, it's 0. This one, it's 24. So if you're looking at a sine or cosine function that's just written out someplace, you can tell a lot about what's going on by the extra numbers that you see. The trickiest one, though, is about computing the period if it's changed. If there's stuff that's done to the input variable, that kind of makes it's a little bit harder to see. And that's where both you'd see horizontal shifts and also period changes. So if we talked about things that have different periods a little bit last week, let's see. Backwards clock was a weird one. All right, so this example is one from the lesson that you already did. But I want to point this out because it's kind of a nice way to think of it. So h of theta equals sine of theta has a period of 2 pi, because theta going from 0 to 2 pi takes you through all the sets of values that it has. So sine of 3 theta, with that extra 3 in there, if you can see, when you plug in a number for theta, it gets tripled before you calculate the sine value. So you can kind of think of that 3 as like a speed at which it goes in there. So I've multiplied my angle by something, meaning if I were to think like, oh, let's say theta goes from 0 to pi over 2. In the sine function, h function, sine of theta, if theta goes from 0 to pi over 2, then my y value goes from 0 to 1, right? Pi over 2 is the same as 90 degrees, or 1/4 of a circle. If I have sine of 3 theta, and I let theta go from 0 to pi over 2, before I calculate the sine value, I'm going to triple it. I'm going to triple that angle. So I'm like, oh, well, if I put in 0 through pi over 2, sine's going to think I put in 0 through 3 pi over 2. So it's going to go through 3 times as much of a circle. If you want to think of it that way, it goes through 3/4 of a circle instead of 1. So if we were graphing these, and let me just pull up Desmos. I don't know if it suggested it on this problem or not, but I'm just going to do y equals sine of x. Looks like that, right? If I have y equals sine of 3x, that's the blue one. It's definitely the same sort of pattern. Let me get this regular x out of the way. So it looks like a sine curve, starts at 0, goes up and down, back up again. But it does, these are just, this isn't 2 pi, this is just 2 here. So between 0 and 2, a little bit past 2, it goes through its whole period. Or by the time I get to 2 pi, which is 6 point something out here, you can see it's gone through 1, 2, more than 3, or about 3. In fact, it's exactly 3 cycles of its graph. So there is a 3 in front of that theta. I'm going to use this race car one again. But if I'm looking at the function sine of theta, theta has to go through 0 to 2 pi. to represent all the way around one loop, or the sine values from going all the way around one circle. On the other hand, if I have something like sine of 3 theta, if I were to plug in 2 theta, that's all the way to like sine of 6 pi. That's whole 3 circles worth. I'd have to plug in something, well, 1/3 smaller, or 1/3 the size, I guess would be the correct way to say that. Because 0 to 2 pi over 3, plugged in the space of where this theta is, would make the argument, the whole input to the sine function, come out to be 0 to 2 pi. So it takes 0 to 2 pi to make sine of theta go all the way through its values once. It takes only 1/3 as many numbers to go through, 1/3 the length along the x-axis or horizontal axis, for theta to go through, or for sine to go through all of its values if I have a 3 in front of it, because, well, I only need to put in 1/3 as much if it's going to get tripled by the time I plug in. So no matter if there's some number in front of the angle, in front of the input variable inside the sine function or cosine function, works equally with either of those. Whatever that number is in front, that like increases the speed at which this goes through, or like how fast, just in terms of like how many numbers you have to go through until it starts repeating. In this case, you can see by the time I get to 2 pi, 6 point something, I have 3 full periods here. And the larger the number I put in front of sine, like if I change it to 5, or 10, or 15, it speeds up how fast it goes through this, or it shortens that period length. It shortens the amount of time by the reciprocal number to what we were multiplying these factors by. So if I put in something like, here's regular sine of x. Let me put in y equals sine of 0.5x, 1/2 x. It spreads this out. In fact, I want to shrink this down so I can see a full period. Maybe I'll make the amplitudes bigger. Here, 10. So we can see this again. But you can see maybe the blue one, which is sine of regular x, goes up and down and back up by the time you get to 6.28, 2 pi. The green one, sine of 1/2 x, up and down and back up by, well, it looks like a little bit past 12. 4 pi. No. Yeah. 4 pi is about 12.56, if I can multiply properly today. But in any case, you can put larger or smaller numbers in place of, or as coefficients on x. I just increase the amplitude here. That doesn't change the period. Let me shrink this back down again. Oops. Yeah, well, zoom back in. I'm going to get rid of this. So if I had, here's regular sine of x. Looking at 1 up, down, and back up. 0 to 2 pi, right here. That goes through 1 period. If I change the amplitude, it doesn't change that. So just, I don't want to have them on there at the same time because it gets messy looking. But if I put an amplitude of 3, or a multiplier on the front as 3, it still goes through 0, 0, goes up, down, and back up by the time we're just past 6, or whatever this number is. If I change that multiplier in the front, that isn't changing where the period starts and stops. It changes the amplitude. It changes how high and low it goes, and it changes how far above and how far below we are at each value, but it doesn't change where the zeros are. Multiplying anything that was 0 by a larger number still keeps it 0. And the period hasn't changed by changing that number in front. Just makes it taller or shorter. So it's like a vertical stretch, just like 3x squared versus regular x squared. It's just that, remember when you're dealing with functions that have x-intercepts, horizontal intercepts, that vertical stretching happens, like things that are above the axis go higher, things that are below the axis go lower. this, you can kind of see the symmetry because it has it kind of in the first place. When you have these, it stretches it vertically, although the x-intercepts remain in the exact same spot. So let me just pick a medium-sized number here. There's 2. Good size for this graph. Now, if I were to do something like add a number to the end, like add 5, it's the exact same shape.
Just changes the origin.
Yep. And I'll put those parentheses in for clarity. So 2 sine of x versus 2 sine of x plus 5, the difference is where that midline is. And you can see this one's up at, goes as low as 3, and as high as 7. I'll zoom in a little farther so you can see what number that's at. But this is between 3 and 7. This is between -2 and +2. So the shape is maintained, the period is maintained, it's just the position that's all shifted upward. But if I were to see this, just that equation, 2 sine of x plus 5. And the reason I put those parentheses in there is because if you're not clear, it might look like that, which this is different. 2 sine of x plus 5, which it's maybe a little bit hard to tell that that moved, but notice that this bottom of the curve is now to the left of the axis a little bit. It's like, why is it to the left of the axis? There's this plus 5. Because it's pretty close to 6, and 6 is about how long the period is. It's kind of hard to tell. But you want to be clear about sine of what? Sine of x. Plus 5 is certainly up here. So in any case, 2 sine of x plus 5, if I were looking at that, I can say, well, the sine function tells me vertical position above or below the center of a circle, if I'm thinking about rotations. So in terms of just radius lengths, it's a maximum of 1 above and 1 below. If I'm talking about like feet or inches or something like that, kilometers, light years, then I want to have the radius of that circle's size represented, that y equals r sine of x, or r sine of theta. This represents the radius of the circle in units, like regular measuring units, not in radius lengths. So if I'm looking at this and say, oh, well, I'm on a circle of radius 2, that's 5 feet above the ground, or something like that. You can kind of, if you want to create a story to go along with it, thinking about this, that coefficient can represent the radius of a circle that you're rotating around. Any number added or subtracted at the end tells you how far above or below the ground, if you're thinking about vertical position, sine functions, the center of that circle is. So 2 sine of x plus 5, you can think, oh, Ferris wheel, 5 feet above the ground, center, and it's got a radius of 2. So, well, it's going to go between then, 5 is the middle, 2 above 5, and 2 below 5. Or if you don't want to create a story every time, you can still say, oh, well, it's going to go up and down by 2 units apart from that midline of 5. So that 5 represents the midline and the 2 is the amplitude. And amplitude, you're going to use both above and below that midline by that amount. So you can see that if you are used to these functions, this is going to go between 3 and 7. Okay. So if you saw a graph without the function to go with it, you might be able to piece together what has to be in that function by where the midline is and how far above and below the midline it goes. Now, there's also like sine versus cosine sorts of issues, but the trickiest part, like I said, is usually the putting extra numbers in here. It can change the period of the function, how it looks, how often it repeats itself. A larger number in front of your input variable multiplied on is going to make the period shorter. A small number, less than 1, is going to make it stretch out, which we don't really have that effect with most other sorts of functions because of like things like distributive property. There's ways to take that out and use it a different way so it all looks like vertical and horizontal shifts still, or vertical stretches or compressions. But with these, it changes how often it repeats itself since it's a periodic function. So we can really see this. So you can think of this, oh, this is a speed of 3. I've sped this function up by a factor of 3, meaning it goes through its paces 3 times as fast or 3 times as often over a given interval. So instead of taking 0 to 2 pi, it only takes 1/3 that time to go through its whole cycle of values. All right, so for instance, this question that is toward the end of the lesson said, what's the period of h of x equals cosine of x over 5, and what does it represent? Well, that over 5 is like multiplication by 1/5. So just like this factor of 3 multiplied on made the period shorter, made it go through all of its values more quickly, left to right, by 1/3 the distance that it would take otherwise. That 1/5 multiplied on means it's going to take 5 times as long to go through all of its values. Because if you can imagine, in order to make this inside part come out to equal 2 pi, I'd have to substitute in 10 pi, because it gets whatever I substitute in gets divided by 5. So 0 to 10 pi would be 1 full cycle of this cosine graph. Or it made the period 5 times as long as it was before, or spread it out left to right by a factor of 5. So in any case, this period of 10 pi represents how much x has to vary by for the input of h to vary by 2 pi. It's just that first answer on there. Oh, actually, it's input versus argument. The argument of h, because we're inputting 10 pi, but the argument turns into the whole thing, the whole inside the parentheses, what we're taking the cosine of varies by 2 pi. Period, sine, and cosine. So there's this whole description of doing this weird computation and what if there's other numbers in there. If you want to find the period, you don't actually have to worry about horizontal shifts for that. You can ignore it. But horizontal shifts are important. They're messy, they're hard to graph, and they're not nice to try to figure out where the equivalent points are. But I did want to point out that, so this cosine of 2 pi over 3 has a period of pi radians. This plus 3 moves the curve left to right or right to left, and actually you can think of it either direction because, well, it's periodic. So if you just look at the final result, it's kind of hard to tell which way it was shifted. But that plus 3 affects the horizontal position of this. It doesn't affect how fast it goes through its values, though, because it's not multiplying the angle by anything. Only that 2 does. So despite there's this whole weird set of computations here, but whether I have cosine of 2 pi or cosine of 2 pi plus 3, the plus 3 inside the parentheses, or cosine of 2 pi minus 1.7, all that computation inside, anything's added or subtracted, those don't affect the period. It's only that coefficient that affects the period. But other stuff in there, though, does affect where maybe your key points would be laid out. And so just for comparison, I'm going to write up 3 functions here. Let's say I have f of theta equals cosine of theta, g of theta equal, or actually let me make this cosine of 2 theta. Cosine of 2 theta minus 1, and h of theta equals cosine of 2 theta minus, let's say, pi over 2. So all of these have the exact same period. They do not all have their periods like, they don't all start and stop like on the x-axis at the same points, but they all have the exact same period. All these have a period of pi units, right? Find a bigger piece of chalk. Cosine of 2 theta, cosine of parentheses 2 theta minus 1, and cosine of 2 theta minus pi over 2, all in parentheses. All of those have the exact same period. 2 pi divided by 2 gives us that period in each case. And 2 pi divided by 2 is just pi. So that tells us the length left to right of a period, or matching points would occur pi units apart, left to right, regardless of where some nice x-intercepts might be, or I guess theta intercepts, horizontal intercepts might be, or the peaks might be. Consecutive peaks of this cosine function graph would be pi units apart someplace. They're all going to be in slightly different positions. And notice the amplitude is 1 on each of these, and there's no numbers added to the end. So the midline is the horizontal axis, y equals 0. Y equals 0, x-axis, horizontal axis, and amplitude is 1 for all of these. So they've got a lot in common. But let me just show you a graph of these, and we'll talk about what on earth that means. So let's see. I have y equals cosine of 2, I'm going to use x here. Let me zoom in a little bit so this is. There we go. So there's y equals cosine of 2x. If I have y equals cosine of 2x and inside the parentheses plus 1, well, that's a little bit of a mess. And if you look at it, it's like, oh, well, it shifted left by 1. Not quite. This is -1. So the top of that red curve isn't 1 unit to the left. We're going to have to figure out how much it is to the left. We'll do that in just a second. But you can see that that -1 inside the parentheses is a left shift, kind of like x squared versus x minus 1 in parentheses squared is a shift. This is a shift also, but we'll figure out how much. Now, this one, y equals cosine of, let's see, 2x minus pi over 2. This one, let me get the red one out of the way for a second. So just comparing, pick a different color. Will it let me? There we go. Sorry, I'm just going to do it this way. 2x minus pi over 2. There, now it's green instead of black and blue, which are too close together to tell. These are still almost too close together to tell. But regular 2x versus 2x minus pi over 2. Regular cosine function has its peak right on the axis here. This one's like, well, did it move left by that far? Did it move right by that far? It doesn't really matter. Either one, it's a periodic function. But I can see that, like, these look nice. They're not like, it's just a shift. It's not a completely different shape. They have the same period. It's just the periods don't line up with the same, like, peak positions. So if I want to figure out where these have shifted to, like how far left or right, that's when we can use that set of computations that you saw at the bottom of that lesson. This is kind of like messy, a little bit messy algebra-wise, but if I want to figure out where the equivalent of 0 to 2 pi moved to, I'm going to set this equal to 0 and set this equal to 2 pi and figure out what theta values that corresponds to. So 0 to 2 pi, let me just do this over here. Or I could use 0 to pi, since that's the period of all of these. But if I'm looking at cosine of 2 theta. I know the period's pi, so I can just use 0 to pi. But if it was something weird, you can always just pick 2 values and see where they go to. And what I mean by that is, if I have zero to 2 pi is normally what I want to plug into a cosine function to go through the whole thing. This will tell me, oh, this corresponds to theta equals 0, and this corresponds to theta equals pi. So this is one way to find it. This is like the computation that they're showing in the red down at the bottom of the lesson to tell you, oh, it goes from 0 to pi, so the period is pi units. But it also tells us that the regular, like, thinking mentally, cosine function that goes like, starts at, let's see, 0 to 2 pi. Starts at the top, ends at the top, and hits its minimum down below. I'm just trying to divide that into x-intercepts halfway between. Like, so that kind of U-shaped thing for cosine goes between 0 and pi. So I can just say, okay, well then if I wanted to graph this, I would just erase that, call that pi, and then make that pi over 2. Now, if I were looking at, instead, that g function, cosine of 2 theta minus 1, well, I want to know what 0 to 2 pi corresponds to. So if I set 2 theta minus 1 equal to 0, and 2 theta minus 1 equal to 2 pi, I can figure out where that translates to in this shortened function by a factor of 2, but with a translation as well, this horizontal shift left or right. So if I solve this, add 1 and divide by 2, I'm going to get theta equals 1/2. Same thing here, add 1 and divide by 2. I'm going to get theta equals, let's see, 2 pi plus 1 divided by 2, which would be the same as pi plus 1/2. If you like split it into 2 fractions, 2 pi over 2 plus 1 over 2. So no, these are pi units apart, that's easy to see. 1/2 and pi plus 1/2 are also pi units apart. Not as easy to see, but that's why I'm like, if you're just trying to find the period, don't worry about where the period happens, just like take that coefficient, 2 pi divided by that will give you the period. But if I wanted to look at, here, let me put this 2 pi minus 1 in here. This says that the period, the equivalent of 0 to 2 pi in a regular cosine function is now 1/2 to pi plus 1/2. If you look at this graph, there's that peak of this function. It's at 1/2. You can see it's halfway between 0 and 1. Here's the bottom, a little bit past 2. But here's the top, and that's kind of hard to see, but where it is, it's like, oh, it's almost at 4. But the original one went from 0 to 2, or 0 to pi, 0 to 3.14. We're half a unit past that. We're looking for pi plus 1/2. So 3.14 plus about 0.5, 3.64. Yeah, that's about where that is. Not really easy to see, but that last vertical divider it went by was 3.6. So 3.2468 and then 4. So you can see, oh yeah, that's half a unit to the right. It's usually easiest just to find the point at 0 where that moved to, because as you can see, that's maybe easier to find. Oh, instead of having its peak at 0, it has its peak at 1/2. So the 0 in this function corresponds to the 1/2 in this function. That's when theta equals 0, or the input equals 0, the argument equals 0. And the original function, and also in regular cosine of 1 theta, is up at that peak. But by putting this minus 1 in there, it moves to the right by half a unit. There is a pattern to these. It's not awful to solve. But let me just show with the other one here, this 2 pi minus, 2 theta minus pi over 2. If I were to do this same thing, just write it up here. Cosine of 2 theta minus pi over 2. Pi over 2? Pi over 2. If I want to know, well, when is this input equal to 0? And when is it equal to pi? Or when is it equal to 2 pi? Whatever you're interested in. You can see that the period comes out to be pi by the distance between them. But yeah.
So for laying things out on a graph like this on x, y-axis, like the units themselves, 1, 2, 3, are those like a measure of radians in this instance?
Yeah, so these are number of radians. So 6 radians, 7 radians, 5 radians, 4 radians. So 6.28 radians or radius lengths is one trip around a regular circle, but I've got my angle multiplied by 2 here. So that's like, yeah, 0 to like 3-ish is all the way around one circle. Yeah, so the input here is the angle, and these are in radians. And the output is this vertical distance or horizontal distance, depending on whether we're talking about sine or cosine functions. We're talking about cosine here, so this would be horizontal distance from the center of the circle if we're measuring circular motion. But again, if I want to know, well, where does the 0 go to here? So 2 theta minus pi over 2, what number would make that equal 0? Like, what would I have to plug in for the angle to be the equivalent of cosine of 0 here? It's like that one. Add pi over 2 and divide by 2. I'm going to do it in 2 steps this time. 2 theta would be pi over 2, so theta would be half of that, pi over 4. So the beginning of this curve is at pi over 4 instead of at 0, or that's moved pi over 4 to the right. This one was moved a half to the right. Or if you can maybe see what goes on with these, it's not like this weird mystery of like every time it's going to be something different. There is like a trick to remember, but you can recompute this from scratch. You don't have to memorize it. Just say, okay, so what points are equivalent to the beginning and end of a period? You can figure out how long the period is by that, and then you can also figure out, okay, where position-wise are these, if I'm trying to graph this, how has it shifted away from where I'm used to it being? And the first one there hasn't shifted left or right, it's just been shortened up from a traditional or basic cosine of theta kind of graph. This one's shifted to the right by a half. This one's shifted to the right by pi over 4. And I say to the right because this is a positive pi over 4. Substituting in pi over 4 to this function would give me the same result as substituting in 0 to cosine of x. So the 0 of cosine of x, or the input of 0 cosine of x puts me at the peak. And for this one with a 2x minus pi over 2, that peak is at pi over 4. So if you can see, the peak of this green graph is directly over this first x-intercept here. This x-intercept is directly over that bottom. And then, so each kind of key quarter point of the function matches up with one of the other. It's just kind of hard to see because they're not at nice numbers, any of them, in terms of they're not whole numbers. But this has a 2 in front. Pi over 2 gives me the period, or 2 pi over 2 gives me the period, division by 2 gives me the period on all of these, it's pi. That number at the end, divided by 2, gives me the horizontal shift. It's the same 2 from before. It's not always 2. For instance, if I change this to 5, and if I'm looking at cosine of 5x versus cosine of 5x minus 1, that shifts to the right by 1/5. So sometimes what you'll see people do in order to make this look more like it did when you're dealing with parabolas and other sorts of functions to see like horizontal shifts is factor out the parts inside the big piece of chalk. I'm going to break it. Factor out the parts inside the argument to have that coefficient in front of everything. And what I mean by that is, instead of writing this as 2 theta minus 1, writing it as cosine of 2 x minus a half, like double parentheses, or not x, theta, sorry. So I can say, oh, yeah, so it's got this, period is changed by this number and it's shifted right by a half. It's kind of overkill, but if you can just remember, if I have, let me just write this in general, because that's just kind of parentheses overkill. But if I have something like cosine of ax minus b, cosine, or theta, or whatever letter you want to use, cosine in general has a period of 2 pi, cosine of x, cosine of theta, whatever I want to call that input variable, has a period of 2 pi. 2 pi divided by this coefficient would give you the period. If this is larger than 1, that makes the period shorter. If this number is a fraction between 0 and 1, that's going to make the period longer. 2 pi divided by like 1/5 was 10 pi. So whatever letters, I just called ax minus b, just because they were the first 2 letters in the alphabet. This would indicate a shift to the right, but it's not by b units, it's by b divided by a. And when it's just like with what we did with like parabolas or other sorts of functions, if it says minus something, it's a shift to the right. If it says plus something, it's a shift to the left. And why that is, like if I want to know, well, what does it take to make this equal 0? Well, it takes bigger numbers, larger x values, if you have something subtracted. So we have to shift to the right to get those same values, or use larger x values. So I'll say shift right. But if b is something negative, like minus a negative something, then it would be a shift to the left. But if you see minus here, you say, oh, shift right by b over a. If you see plus b plus something, you say, oh, that's a left shift by b over a. You don't have to do this double factoring, but it will always come out to be that same sort of like shift where you divide by this to get the period properly. You're also going to divide by this to get the shift properly. Just take 2 pi divided by that coefficient to get your period, and this number divided by a to get the shift. You can factor it out, and you'll see that written in some places, but it looks like a lot of parentheses. It's a little bit confusing. Is there anything else? Oh, so this stuff in red now. Back to this, because it looks like a mess. This is talking about the function cosine of 2 theta plus 3, where you can say, okay, so when does this 2 theta plus 3 equal 0? When does it equal 2 pi? And the distance between those two numbers tells you the period. But you can also figure out where the beginning and end of your numbers that you're used to for cosine appear on the graph. So where it starts at the top and then goes down and back up to again. So in this one, we get the period isn't 2 pi minus 3 over 2. That's why it's in red. But 2 pi minus 3 over 2 is the equivalent of the endpoint. It's the x value or the horizontal value at the end of that first period. 2 pi, let's see, that would be pi minus 3/2. And I don't know what that is as a number, but it sounds like it's about 1.5 overall. So like 3.14 minus 1.5, it's like 1.6-ish. So the right endpoint of this should be like around 1.6, of the right endpoint of the first period, the top of that next hill. Whereas the left endpoint would be as if I put in 0 here and solve, which would give me, or set this equal to 0 and solve. So it'd give me negative 3/2. So negative 1.5 through about 1.6 for cosine of 2 theta plus 3. Cosine, y equals cosine of 2x, because it's used type, plus 3. Let's see. All right, the period is still points that I can reach. A little bit past 0 to a little bit past 3. Okay, that's about 3 units, so that's still a period of pi, like we were talking about before, but just looking at it visually. So that's by doing 2 pi divided by 2. 3 divided by 2, and it's a positive, so this is a shift left by 3 divided by 2, or a shift left by 1.5. Instead of this peak being on the y-axis, you can see that there's a peak at negative 1.5. And there's also a peak here at 1.6 something. That'd be the end of the next one. These two peaks are pi units apart, just like the two bottoms that I could reach. Those are a bit too high for me to reach. But in any case, from peak to peak, trough to trough, corresponding x-intercepts, not every x-intercept, but from like the x-intercept where it's headed upward to the next x-intercept headed upward, those are pi units apart. All the matching pieces are going to be pi units apart. That's that period. The amplitude on this right now is 1. Now we made it 3. Those are just multipliers. Now we're not going to deal with this too much, but you can have negative amplitudes also, which that flips, like if I had 2x, or 2 cosine, here let me just put in a regular cosine function. Negative 2 cosine of x, as opposed to positive 2 cosine of x, that's just a vertical reflection, just like a negative in front of anything else. We're not going to deal with that too much, but the same rules apply to those sorts of things as previous. The weird aspects of these periodic functions is finding the period, first of all, and those horizontal shifts, since it's not a fixed shape like with one vertex that you can just track where it goes easily. It's got infinitely many wave tops, and trying to figure out where they go when they repeat every so often, it's a little bit of a task. So goal for today was to kind of look at what various numbers in different spots of trig functions, sine and cosine particularly, do to these amplitude, vertical shifts, and midline. Those are maybe the more easy to recognize. Midline is going to be 0 unless you see something added or subtracted as a constant at the end, which shifts it up or down, just the direction that it looks like. Like plus 7 makes all the y values 7 larger. Amplitude is represented by those coefficients, multipliers onto the cosine or sine function. Period and horizontal shifts are the messy parts that deal with what's inside the argument to the trig function. Cosine of whatever's in parentheses, sine of whatever's in parentheses. But the coefficient on the variable in there is like that speed. A larger number there indicates that it goes through its period more quickly than 2 pi, or the period is shorter. And a number smaller between 0 and 1 in that position, we're not going to deal with negatives there because, again, there's not really a need to deal with putting negatives in those positions because it is a periodic function. If you want it to go down first then up, you can also just shift it to the side. Has the same effect. Because if I look at this function, like, oh, well, that looks kind of like it's a sine function that starts here. Yep, or it's a cosine function that's been flipped over. Or it's, you can always just use sine functions and ignore cosine completely if you want to draw a graph that matches one of these waves. Just sometimes one is easier to pick than another. But this coefficient of the variable in the argument, if you do 2 pi divided by that, it's going to tell you the period of your new compressed or stretched horizontally function. And any number added or subtracted inside that argument, any constant added or subtracted divided by that coefficient, even if it's 1, is going to tell you about the horizontal shift. A negative, so like minus 5 or minus pi over 2, is going to indicate a shift to the right by that number divided by coefficient. And a plus, so like plus 0.5 or plus pi over 7, is going to indicate a shift to the left by not that number itself, but that number divided by that coefficient. Because we can always solve what's the equivalent of 0 to 2 pi for this function. You can just do it from scratch and figure out what the period is, the distance between those two numbers, and where the starting and ending point are. But you can, so you don't have to memorize all of this that I'm telling you, but just summary-wise, it does turn out the same every time. It's just a matter of, is it an easy to remember pattern for you, or do you need to like see it worked out from scratch? You can go either way about it. It's up to you. It doesn't really take a lot of extra time, but if you see a function, just say, oh, look, I know the period, I know where it's at, I can kind of picture this, or I can see what this is representing, how high and how low this goes. All right, so I'm going to stop at that for today. That's a lot of just random numbers, but I hope that that was helpful graphically to picture what's going on. What you're going to see in the assignment is about periodicity, like figuring out the period of various functions, doing computations involving where's the midline, what's the maximum and the minimum then, so like how high above, how low below that midline are we going to go, and then looking at graphs and talking about where they're shifted to, shifted upward, shifted left, right, etc. So see what you can do with that, but like I said, I left the, let's see, let me go back to the calendar here. So I left the homework is still due, but 7.7, the lesson isn't due till Monday, so you have some extra time on that, but the homework isn't going to be due till I see you again. That's where more of the period stuff and the weird shifting is in that 7.7 assignment. Let's see, periods, amplitudes, shifts. Oh, so next week we'll be talking about the tangent function on Tuesday after we finish up a little bit more with just going over the results of all of this fun stuff. We'll have a worksheet that we'll do in class on Tuesday. We talk about tangent function, which is about, circular-wise, about the slope of the terminal side of an angle as it goes around. So it starts out as a slope of 0, increases through positive numbers, becomes undefined, and then is suddenly extremely negative, and then it continues until it's positive again, etc. So it also repeats, but it goes through some undefined points. So it's not a wave curve. It is just a wiggly line with some undefined spots. Infinitely many vertical asymptotes in reality. We'll talk about tangent function on Tuesday, as well as probably some, let's see, a little bit of right triangle trig. Trying to think of what else we might need. But finishing up chapter 7 during next week. And as I said, the test is mostly going to be chapter 7. Even though it is not until, so here's, let's see, yeah, that's next week. The test isn't until 2 weeks after next week. We'll finish it's mostly just going to be chapter 7 or module 7 stuff. There's a little bit about right triangle trig, which will be a little bit of Thursday, next Tuesday. But keep in mind there's this gateway assignment. It's just some like technical algebra skills sorts of things. There's not really good story problems to go with them, but they're just kind of good skills you've probably learned before. Chance to brush up on those because you will need them in calculus. Lots of it is stuff that you won't even see till calculus 2. Weirdly, there's more there's more algebra involved in calc 2 than calc 1, but they're good things to know. So I just kind of put them in there to work on these rather than let's spend time in class reviewing algebra. So in any case, that's that. Have a great weekend, and please visit Pathways Tutoring office hours if you need assistance, or email, or post in the forums, or message me, or whatever it might be. All right, next time.